Namaste and welcome back to the Data Structures and Algorithms classes. Today, my dear friends, we are going to explore the world of prime numbers. Now, what do you mean by prime numbers and what makes a number prime if you ask me? Very simple. I'm just showing you a few examples of prime numbers 2, 5, 7 and 11. One thing which all of you must understand is a prime number is a number which has exactly two factors or two divisors. What is a factor or a divisor? It is something which can perfectly divide a number. 2 can only be perfectly divided by 1 and the number itself which is 2. 5 can only be perfectly divided by 1 and the number itself which is 5. 7 is 1 and 7, 11 is 1 and 11. So clearly you can notice a prime number is such a number which has two factors. And what is important about those two factors is it is the number 1 and the number itself. These are the only two factors it will have. Now let's begin by understanding how to write a program to check whether a number is a prime number or not. Alright, so listen to me. I'm just listing few numbers maybe from 1 to 13 like this. On the other side I'm just listing down the factors. Now look at the factors. 1, which are the numbers which can perfectly divide 1? Only the number itself which is 1. 2 is 1 and 2, 3 is 1 and 3, 4 is 1, 2 and 4, 5 is 1 and 5, 6 is 1, 2, 3, 6, 7 is 1 and 7, 8 is 1, 2, 4, 8, 9 is 1, 3, 9, 10 is 1, 2, 5, 10, 11 is 1 and 11, 12 is 1, 2, 3, 4, 6 and 12 and 13 is 1 and 13, right? Now, I'm just coloring all the non-prime numbers in one color. I'm coloring all the prime numbers in one color. Now, our objective is to tell whether a number given to us, let us assume n, whether n is prime or not. I hope you're able to think. Now, one way that I would approach this is, I would look at the factors because it is the factors which determines whether a number is prime or not. And if I look at the factors, one thing which is clear to me is, every number, be it prime or non-prime, has 1 as a factor. So 1 cannot let me decide whether a number is prime or not. So I'm just removing 1 from the factors. Next thing that you can observe is that every number, be it prime or not a prime number, has the number itself as a factor. So the number itself is not going to help me decide whether it is prime or not. So from the factors, I'm going to remove the number itself. If I remove the number itself, something interesting has happened. Look at all the prime numbers. They don't have any factors, empty. They don't have any factors. If you removed 1 and the number itself, no more factors. Now some of you will be saying, look at 1. 1 you have colored it as non-prime, but it doesn't have any factors. So does that mean it is prime? No. Long back mathematicians have told that 1 is neither a composite number nor is it a prime number. It's a weird number. Okay, so let us not consider 1. I'm removing 1, which means the first prime number begins from where? 2. I will be able to think. So if you look at it, 2 has no factors, 3 has no factors, 5 has no factors, 7 has no factors, 11 has no factors, 13 has no factors. Whereas all the other numbers definitely have factors. I hope you're able to think. And one more thing which you can notice with the numbers which have factors, which is the composite number, is the least factor is 2. From 2 onwards only it goes. I hope you're able to think. Which means if I have to write an algorithm, how would I do that? Given a number n, second step what I will do is run a loop from I, which begins from 2 because the least factor is 2, and I will go till where? And now that till is an important part. Look at this and tell me. Look at every one of the last factor of these numbers. Look at the last factor of every non-prime number. Do you see the last factor is actually nothing but the number divided by 2? Are you noticing that? Look at all the non-composite, non-prime numbers. Look at the last factor. It is a number divided by 2. I'm just highlighting those numbers for you. See, it is a number divided by 2. Which means, wouldn't you agree that I can start from 2 and I don't have to go to the number itself. I can stop at n divided by 2. Now inside this, what will I do? According to my logic, if there are no factors, it is prime. If there is a factor, it is composite. which means I'm coming here and I will just check if in case this number has a factor or not, or is I value a factor or not. So what will I do? I'll just check if in case, take the n value, divide it by the I value, check if the remainder is equal to 0. If the remainder is equal to 0, 100% it is a non-prime number, and hence I will return false, meaning it is not a prime. But out of the loop if I come successfully, then I will return true, because it means not even a single factor was found and all our prime numbers are factorless in our approach. I hope this algorithm is clear to you. Now some of you will be thinking this itself is a very efficient way of calculating prime numbers. It certainly is not. There are much more efficient ways. What are those? I will show you, but let us quickly go and write code for this. Let's write the code in Java. I'll just create a static function which returns a Boolean value, true or false, is it prime or not. And I would like to call this function as isPrime. That is its duty, to tell you whether it is prime or not. And it will accept just a number n. Inside that, now comes my logic. Bring the bracket down. So see here guys, what I'm going to do inside this is very simple. I am going to run a loop. So I will tell for. According to our logic, I should begin from 2. And then it should go till I less than equal to n divided by 2. That is where it should go. One by one it should increment. So I plus plus. I'll come inside that, and what I'm going to do here is very simple. I am now going to just check if I is a factor of n. How will you do that? I mod n or n mod I. N when divided by I, is it 0? Is it a factor or not? According to our logic, even if a single factor exists, then it is not a prime according to our logic. So I will return false. Now, if the control comes inside this even a single time, control will come out of the complete function, which means if I iterated from 2 till n divided by 2, not even a single time the condition was satisfied, I will come outside the loop. If I come outside the loop, what is the meaning? It means that it is a prime number. So I will return true. Any confusion till here? Yes, we understood. I'll come down, and in my main method I'll just create a scanner object, and I am going to give it a reference. We'll call it a scan. I'll also just import it. Yeah, great. Next I'll just scan the number n from the user, so it's an integer variable. All prime numbers are integers. I'll tell system.out.println. I will call my isPrime method and I'll pass n to it. Great. Will this work? Let's check it out. If in case I execute, then let's start with the most basic prime, which is 2. True. I'll re-execute, and if in case I tell 13, true. If in case I tell 6, false. So it works. Perfectly it works. Now the question is, what could be the time complexity of this code? Let's go explore. The analysis of time complexity is very simple for this, right? So first thing is, how many times will this loop work? Because it's going from 2 till n by 2. So if it was going from 1 till n by 2, you could have just told n by 2 plus 1 directly, you could have told. But since it's starting from 2, it is not like that. Watch it. I'm just taking an example. Assume n is 13. So you will start from 2. Right? So I starts from 2. 2, then 3, 4, 5, 6, it will go till n by 2. n by 2 is nothing but 6. I hope you're able to think. That is 6. Then the false condition also, which is 7. So if you look at it, 1, 2, 3, 4, 5, 6 times. So 6 times it is working, which is nothing but n by 2. So how many times is this working? N by 2 number of times. So that is why I'm just going here and writing that for you, that this will work for n divided by 2 times. Whatever is inside this, that is this if condition. Whenever you enter, this if condition will work, which means it will work 1 time lesser, because this also takes into consideration the termination condition, and hence it is going to be n divided by 2 minus 1. Please remember, all return statements will execute only once, because the meaning of return is the moment it will return, control comes out of the function. So this executes once, this executes once. And you already know constants don't matter to us, which means if I add it, I will get something like 2n divided by 2. There also again, if I remove constants, my time complexity will be big O of n. And you all know that the moment you see big O of n, this is the graph that should come to your mind. It's linear complexity, linear complexity. So is it efficient? While coding it, while coming out with the logic, you thought, oh, I have, removed all ones, I've removed the last factor, I'm going only till n by 2, very efficient. Where? As the size of n increases, the time will also increase. It's linear in time. And prime numbers being such an important component of coding, we cannot be finding prime numbers in linear complexity. Clearly, there must be more efficient ways to do it. What are they? Let me show you. All right, let me now talk about the more efficient approach of finding prime numbers, right? It's very easy. See, we are starting from 2 and we're going till n divided by 2. But my question to you is, should we really go till n divided by 2, or can we go somewhere before itself and stop and find whether it's a prime number or not? You actually can. How? Let me show you. Guys, watch it. Ultimately, this loop is trying to find whether there is a factor, which means in this loop, you're checking whether it is not a prime number, and only when it comes out of the loop, you're telling it is a prime number. So let me take few non-prime numbers, 9, 15 and 25. Okay, now look at this. If in case we take 9, so this loop will start from 2 and go till n divided by 2, which is nothing but 8 or 4. Would you agree with me? And for 15, it will start from 2 and will go till n divided by 2, which is 7. For 25, it will start from 2 and will go till n divided by 2, which is nothing but 12. I hope you're able to think, right? So now I am saying, look at this. This condition will become true for which value? Let us see. For 9, this condition will become true for the first time when it becomes 3. I hope you're able to think. When it becomes 3. For 15, the first time you will find a factor is when I value becomes 3. I hope you're able to think. For 25, the first time that I, or the first factor that you will find is when I becomes 5. I hope you're able to think. Now there is something really interesting here. I want you to think about it. Now this 3 that you saw, don't you think I can say 3 is root of 9? Don't you think for 15 you found 3, right? Now root of 15 is 3 point something, which I can round figure write it as 3. So again it is root 15. Don't you think 5 is root of 25? Which means in general, can I say that the first factor you will find when you check till root n, root n, root n, root n. I hope you're able to think. So what is the need to go till n divided by 2 when the first factor you will find will be somewhere where root n, somewhere at root n. And don't think I have proved this. No. Already mathematicians have proved it. I am just helping you understand that the first factor will always lie at the maximum at root n or before that. I hope you're able to think. Which means no need to start from 2 and go till n divided by 2. You can go till root n. I hope you're able to think. And that is what I am also just showing you, that there is absolutely no need to go till n divided by 2 when one can easily go till root of n. I hope you're able to think. Till root n you can go. Any confusion till here? Really, will this make my code more efficient, and will this logic really work? Let's make the changes and explore. Alright. The aim is to replace n divided by 2 with root n. Now the question is, how will you calculate root n? Now there are built-in functions. In Java, you can use the math class, and inside the math class you have the sqrt function, right? So that is what I'm going to do, math.sqrt. So I'll just go there and I will tell math.M, because it's a class, math.sqrt. I will tell. Square root of what? N. That's one way to do it. If you want, you define the sqrt function on your own, right? And you can always call that function. Anyways, will this work and will it actually give me the desired result? Let's execute and check it out. Okay, so I'm just going to go here, and if in case I execute it and I give it as at 13 is certainly a prime number, I will get the answer as true. If in case I give 25, which is not a prime number, clearly you can see I've got it as false. So it works, but the efficiency has clearly increased. Now, no need to sit and overcomplicate all this. Previously, we were going from 2 till n by 2, right? When it was going from 2 till n by 2, it was big O of n. Now you're going from 2 till root n, which means easily everybody can predict that even if I were to use the frequency count method, I would understand that it is going to be big O of root n, right? And this is how the graph would also look. As you can see, clearly it is more efficient than the linear time complexity that we saw previously, and I'm also putting that linear line to show you the difference, that as n increases, the time is not increasing as drastically as it did in the previous linear complexity. So I hope this is also clear. But can it get more efficient than this? Well, let's explore. Now the question is, can we make the process of finding whether a number is prime or not even more efficient than the last two approaches? The answer is yes. For that, you must now think like a mathematician, and you must try to identify certain patterns which numbers automatically reveal to us. What do you mean, you may ask? Let me begin. Is 1 a prime number, friends? The answer is no, right? All of you know that. So don't you think in my code I can just put a condition saying that if in case n is equal to 1, return false. We know it's not a prime number. Next, if you look at 2 and 3, 2 is prime, 3 is prime. And what is unique about 2 and 3 is they are the only two prime numbers which come consecutively, one next to the other. So we know that there is something special about 1, something special about 2, something special about 3. In other words, this first 3 people are really special to us. I hope you're able to think. So I would like to first itself check if n is either 1, 2 or 3. If n is 1, false. If in case n is equal to 2 or n is equal to 3, we know they are prime numbers, so we will just return true. So I have taken care of these 3 numbers. Now I have all these other numbers left out. I have 41 other numbers to check. I would like to reduce the numbers who I am going to check as much as possible. I don't want to limit my range to n by 2 or not even root n. I want to reduce it even more than that if possible. So how will we do this? Now listen to me and tell me guys, is any of these numbers prime? You would say no sir, none of them are prime. Tell me, is any of these numbers prime? You would again say no sir, none of them are prime. Tell me, is any of these numbers prime? Again you would say definitely no, they are also not prime. And tell me what is common between them. 8, 14, 20, 26, 32, 38, 44, 4, 10, 16, 22, 28, 34, 40. Look at what's common. Don't you think each of these numbers, which I have highlighted in a yellow color, are divisible by 2, right? So if n was 8, and I had to check if it's a prime number or not, if I were to just divide it by 2, and if the remainder was 0, clearly I can tell it is not a prime number, right? So same thing applies for this, same thing applies for these numbers, same thing applying for these numbers. So any number which is divisible by 2 is not a prime number for us. Now you may ask, sir, 2 is divisible by 2. Correct, but we've already taken care of that. The flow of control goes from top to bottom. Already we are checking for 2, so such an issue will never come for you. How are we able to think? Great. So this is taken care of. Now tell me. Is any of these numbers prime? Definitely you will say none of them are prime, sir, because they have more than 2 factors. Again, one thing you can notice is like this, don't you think this sequence will keep going downwards? Any number of numbers. So whichever numbers will come in this column are not going to be prime. That's how numbers repeat themselves. And one thing I can see is 3 can be perfectly divided by 9, so can be 15, 21, 27, 33, 39, which means this entire column numbers are all perfectly divisible by 3, which means these yellow lines and this blue line numbers, I need not check if I just put a simple if condition in my code wherein I will check if the given number n is perfectly divisible by 2 or the given number n is perfectly divisible by 3, then return false, because I know it will fall in one of these columns and I know it will not be prime. Which means, do you notice so many numbers we have eliminated? Now what is remaining are these unshaded numbers. Now what could be the logic here? Look at this carefully. Let me start with 5. See, 5, now when does the next digit come, guys? Next digit comes 2 positions later, 1, 2. 2 positions later. So if I were to start from 5, I have to check the ith element and I plus 2 element. 5 and 7 I have to check if they are prime. Are you able to think? And you know how to check if they are prime. If you just check if they have a factor or not. I hope you're able to think, right? Similarly, the next element, see the next element. So let us assume I started from here, right? I plus 2. Now the next element is after 1, 2, 3, 4, 5, 6. Which means I value, I have to increment it by 6. Imagine every step is by 6. So by 6 I will reach 11 and then 11 and the next alternate element, which is 30 plus 2. And then see 11 plus 6. Check this plus 2. Again 17 plus 6. Check this plus 2. Again 17 plus 6, 23 plus 6, 29 plus 6, 35 plus 6, and all alternate elements we are checking. So do you see, if our loop is going to jump by 6, 6, 6 every time, don't you think it will become much more efficient, Okay, now I should start from 5, we understood. Now I should go till where? Till where means root n, because whatever we learned previously still holds, that the first factor will come somewhere at the maximum root n or before. So you need not increase the boundary condition. It can be if I equal to 5, where I was starting from 2, you can make it as 5, because those conditions take care of 2. 5 till root n, but every time I should jump by 6. I hope you're able to think. So all you have to do is whatever I value plus 2. Check if they are prime. Make I increment by 6. That value plus 2. Check if they are prime. Again increment by 6. Like that you can go on. I hope everybody got an idea about this. Shall we go implement this as code? Watch and watch carefully. Let's write some code. Now if you look at this, I will create a separate new function first. We'll call it as static boolean. Okay, check prime. We will call it as check prime. Awesome. Again, we'll take n only. Now, see how I will write. First of all, if in case n is equal to 1, directly tell it's not a prime. So, if in case n is equal to 1, then just tell return false. Good. Next, we'll take care of these two special prime numbers which appears consecutively. So, I'll just tell if in case n is equal to 2 or n is equal to 3, return true. Awesome. Now we have taken care of these guys. Okay. Now we need to completely eliminate these yellow color lines. If the number n falls in any of these yellow color lines, immediately tell it's not a prime. And we know it is nothing but n whether it is divisible by 2 or not. So just come there and I will check if in case n, if in case you divide it by 2 and you get remainder as 0, then 100% will fall in one of these lines. So I will return false. I'll just return false. But there is also one more line, the blue line. And if the numbers line, any of this blue line also, it's not a prime. And that blue line are numbers which is divisible by 3. So I'll just go there and I'll put one OR condition. Why to write unnecessary ifs? Or n mod 3 if it is equal to 0. Then false, which means we have eliminated all of them. Now comes our looping. So see, I will tell for I'll tell I, please begin I from 5. See, now my aim is very simple. Whatever number n is given to me, I want to see if 5 and 7 are they factors. Then I want to jump by 6. Then I want to say if 11 and 13 are factors. Then I want to jump by 6. I want to see if 17 and 19 are factors. And you know, according to our logic we are building so far, even if one factor exists, then it is not a prime number. I hope you are able to think. So see, I'll tell for I starting from 5. Now, till root n only you should go. I less than equal to root n. This previously anyways I have explained. So math dot square root of n. Right? See guys, you can write like this also, or if you don't want to use built-in function, very simple. Let us assume you remove that, yeah. See, here you have something that looks like this. You have you have I less than equal to root n you have. You want root to be removed. So what will you do on both sides? Don't you think you'll apply squares? If you apply square, then this will become I into I less than equal to n, because you know square root and this gets cut. So easy way to write this is I into I less than equal to n. I into I less than equal to n. So if in case they don't allow you to use built-in function, then I plus plus, no, I plus 6, every time 6 times you have to increase. Cool? Okay, next. Awesome. Now what you have to do is very simple. You just have to check if in case whatever number n is given to you, if I divide it by I, is the remainder 0? Okay. Now I value, you need not check for the next I value, you have to check for the alternate one, plus 2, because we have eliminated all the other numbers. Or I'll check if 7 is a factor. So I will tell n mod I is equal to 7. Is equal to 0. Not I, because you know, if I is 5, plus 2 is 7. So n in brackets you can tell I plus 2. I plus 2 you can tell. So alternate values you're checking. If that is the case, come inside and just mechanically tell no, it is not a prime because it has a factor. So return false. Return false. I hope you're able to think. Now, if this condition never was satisfied and you never came inside this, you come out of the loop. It means that n is a number which did not have any factors, and according to our logic, that is a prime. So I'll just tell return true. Now, one thing I want you to understand here is that before we execute it, I'll execute it. Okay, fine, let's execute it and see whether it works correctly. Okay. So you can notice, I'll give 25. Is it a prime? No, false. I'll give something like maybe 41. Is it a prime? Yes, so true. So it works. In fact, this 5, 11, 17, 23, 29, 35, 41, all of them are prime numbers. And there is something interesting about them. 5 plus 6, 11 plus 6, 17 plus 6, 23 plus 6, 29 plus 6, 35 plus 6. Now, such prime numbers are only called as your sexy prime numbers. Yeah, I don't know why they named it that, but maybe they are, who knows, right? Because it has increments by 6, so some great mathematician on alcohol maybe named it that way. But anyways, I hope you have understood how this works. Any confusion till this point of time? So also we have something called as cousin primes, right? 5 and 7 are cousins because not directly related. Somebody is there in the middle, from them that fellow came, so cousin. So cousins, okay? So anyways, like this, if we start analyzing numbers, we can continue one entire class that way. But anyways, I hope till here things are clear. Now complexity, time complexity. Please close this. See guys, whether you increment by 6 and all, it doesn't matter. When you analyze complexity, you will look at this boundary condition only. And in the boundary condition, you're starting from 5, that's okay. But you're going till root n only. And when you analyze time complexity, you will anyways remove the constants and all of that. So ultimately, if you ask me, what is the complexity of this? This will also be big O of root n. Big O of root n. But because you're jumping by plus 6, plus 6, plus 6, this big O of root n, this code's big O of root n will be much more efficient than the previous code's big O of root n. I hope you're able to think. Anyways, so all the approaches to calculate prime numbers in a very efficient way, I have told you. But are there more efficient ways? Well, you go do your research. But our discussion on primes has not stopped here. There is something more that we have to learn. What is that? Stay tuned for more.